Here's a puzzle from the end of the First World War. Fishing in the Adriatic Sea just stopped. Boats stayed in port. So when the biologist Umberto d'Ancona looked at the catch, he expected every kind of fish to bounce back together. But that's not what he found. The sharks, the predators, had exploded. Far more than before. Why would less fishing favor the hunters? D'Ancona took the riddle to family. His father-in-law happened to be Vito Volterra, one of Italy's great mathematicians. And around the same time, an American named Alfred Lacca had been chasing the very same idea. Neither of them watched a single shark. They just wrote down two equations. So let's set the stage. We track two numbers over time. Call the prey P, think rabbits, and the predators G, think foxes. The rabbits eat grass, and there's always plenty of it. The foxes eat only rabbits. Take the rabbits away, and the foxes simply starve. Now the rabbits. Left alone with grass everywhere, their numbers just grow. The more rabbits, the faster they multiply. That's the term, a times P. But every time a fox meets a rabbit disappears. And the number of those meetings is proportional to rabbits times foxes. The more of each, the more encounters. So we subtract B times P times G. The foxes are the mirror image. Every rabbit caught feeds a fox and makes more foxes, so their growth is C times P times G, driven by those same encounters. But with no rabbits around, foxes die off at their own natural rate. That's minus W times G. Two equations. That's the entire Lacca-Volterra model. Here's the first question you always ask. Is there a state where nothing changes, where births exactly cancel deaths? Set both rates to 0. Ignore the boring, empty world. What's left is one special balance. The prey settle at W over C, and the predators at A over B. Now watch a small trick that makes everything clearer. Measure each population not in raw numbers, but as a fraction of its balance value. Let X be prey over its steady state, and Y be predators over theirs. In these new variables, the balance point sits neatly at 1, 1, and the equations get simpler. X grows when Y is below 1, and Y grows when X is above 1. Now the real magic. Divide one equation by the other and time drops out completely. What's left connects only X and Y, and it can be integrated. You get a single quantity that never changes as the system moves. A conserved thing. Physicists would call it a kind of energy. Think about what that means geometrically. That conserved quantity is a landscape, a hill with a single summit sitting right over the balance point. As the populations wander, they can't climb or descend the hill. They're stuck on one height, and a fixed height around a single peak traces a closed loop. So every trajectory is a closed orbit. So here's the phase portrait. Prey on one axis, predators on the other. Every starting point launches you onto a loop that circles the balance point and comes right back to where it began. Bigger swings, bigger loops. The system never settles. It just goes around and around forever. Let's walk one lap. Start with few of both. Rabbits have food and few enemies, so they boom. All those rabbits feed the foxes, and the foxes boom next, but they lag behind. Now the swarm of foxes eats the rabbits down. With prey vanishing, the foxes starve and crash too. Few of both again, and the whole cycle restarts. Unroll that loop against time, and you get the picture d'Ancona was missing. Two waves, prey and predators, rising and falling forever. And notice, the predator wave always trails the prey wave. The peak in foxes comes after the peak in rabbits, because the hunters need the boom before they can cash in on it. And here's the twist that cracked d'Ancona's puzzle. Fishing removes prey and predators alike. Run the numbers, and the long-run average of the prey barely moves, but the average number of predators drops. So more fishing quietly favors the predators, the sharks. Stop fishing, and the balance tips back toward the prey. That's exactly what he saw. 2 lines of algebra, no biology at all, and out falls a rhythm that shows up everywhere. Lynx and hare, foxes and rabbits, even boom and bust in markets. Predators and prey, locked in an endless chase, circling a balance they can feel but never quite reach. Sometimes, two little equations no more than a whole sea of fish.